That's all fixed. Oh. Can we
Oh, there we go. Okay. All right. Well, let's get started. Howdy, everyone. My name is Charles, and today I'm going to be giving a talk on decompilation. So let's get right into that. First of all, if you haven't done it yet, please do attendance. That's the QR code on the left. And the QR code on the right is Fire Talks. For those of you who were with us previously, you already know this, but for everyone else, at the end of the semester, we like to give everyone like 5 to 10 minutes to talk about their projects that they've been working on for the semester. It's a lot of fun. Doesn't have to be security related, really, just anything you're working on. Anyways, put it on your resume that you talked about a project. Like, it's too easy. We make it so easy and no one ever signs up. Okay, so what is decompilation? First of all, it is a subset of reverse engineering, for those of you who know what that is. What reverse engineering is taking a binary, which is, that's like an executable file, a .exe, or like an ELF file or something, and attempting to understand the structure of that compiled code and what it does and how it does it exactly. What decomp does is it goes one step further and it says, instead of just understanding how the binary works, we want to reconstruct a set of source code files that when you compile those, it will perform the same actions as the original binary. And then matching decompilation is just one step further, and you get the source files, but when you compile them, your goal is to create an identical binary, which is a lot harder. So let's get into that. First of all, decompilation requires a very, very strong understanding of assembly in whatever assembly language you're choosing to decompile from, because the general steps of it is you get your binary and you run that through something called the disassembler, which takes all the hex instructions and then spits out an assembly file, which is text that we can read, kind of. So just I'm gonna give a bit of an ARM recap. I did want to do MIPS because over the summer I worked on a decomp project for Ocarina of Time, which is a Nintendo 64 game, and that was a MIPS platform. So I wanted to do that, but I couldn't find any functions that were easy enough to fit in, so we're going with ARM. If you don't know, basically what assembly is it's like underneath all the code that you're writing in user space, and it takes all your data that you're trying to operate on, and it sticks them in little containers called registers, which are physical locations on the CPU. So there's a finite amount of them, so you have to make sure that you're not wasting any space. And B, you have to manually load data into specific registers and whatnot. So in this first example here, this is C or Java. I mean, this would compile in 1,000 different languages, but we've got this integer named R3, and we've got these other presumably integers called R1 and R2. And what this assembly instruction in ARM does is it takes R1 and R2 and it adds them together, and then it stores them in R3. Just for convenience, I called all these variables R1, R2, R3 because that's what they're called in ARM. Like all the assembly, a lot of the registers start out with R. And for the second line here, we've got R0 equals 5, This is an old version of the PDF, sorry. This should say while R0 does not equal 0, we're going to do something. And when you translate that to assembly, it's going to store the literal. This is what the hash means in R. It means this is a literal, like just a number, nothing fancy. And we're going to store that into R0. The 0x is just a hex prefix, so it shows that this is a hex number and not a decimal number. So we're going to store the value 5 in R0, which is exactly what this does, right? And we've got this thing called a label, which is kind of just a point in the code that is known and that you can jump to. And I'll get to why that's important in a second. But yeah, I should have written this example better because it doesn't make sense. Is there a marker? There's no markers. Pretend this is a for loop, and pretend it makes sense, and pretend I spent more time preparing. Anyways, yeah, so right here this instruction would subtract 1 from R0, then it would compare the two, R0 and the number 0, and it would set some flags, whether the comparison was a less than or greater than or whatever, and then we're going to branch if they're not equal, which means that if this comparison said that these two things are not equal, then we're going to branch back to the loop label. Again, if I had written this in a way that made any sense, then this would be a lot better of an example, but this is something of a loop right here. What this would do is it would do something 5 times, right? 5, 4, 3, 2, 1, maybe 6 times. Anyways, that's enough of that. Let's do it. Let's just do the real thing that I didn't explain too well. Okay, so what is this? This is a website called decomp.me. It's very, very useful because it will let you, I should, if y'all want to follow along with this, you can go to this website right here. You'll get the same exact thing that I'm looking at. But what decomp.me is it's a little website that holds a bunch of compiler binaries for old Nintendo platforms. And it helps you like decompile individual functions and share them with people if you're having trouble, which is really convenient. So all of this is ARM code, and this is the skeleton of the program that compiled into this ARM code. And together, real quick, we're just going to go through it, and we are going to decompile this assembly back into C. If you don't know C, that's okay. Most of it doesn't matter. Yeah, okay. Just wrote all my instructions. What's up? Yes, sorry. The entire website? Like, is that good? Yep. Okay. Okay, so first things first, we've got this push, LSLS, and LSRS. Here, let me go back here. We're going to go over quickly these few ARM instructions that matter. This push instruction will take a list of arguments, which should be registers, and it's just going to push the values in those registers onto the stack. If you don't know what stack memory is, I'm sorry. It's a stack. You put things on top of each other, and you can push data onto the top, or you can pop it off of the top. If you haven't taken data structures, this isn't going to make very much sense, and I apologize. LR, that stands for link register, and what it's going to do is it's going to hold the program counter, which is basically just a little number that tells you which instruction the CPU is currently looking at. Sorry, that's not an instruction, that is a register that holds that value. Logical shift left, if you've ever seen in code, if you have like an int x and equals 5, you can do this, and that's 5 times 2 to the power 5. Basically, it just takes the binary representation of your number and it shifts it left however many places you tell it to. which multiplies it by 2 every time. So LDR, it stands for load address, and it's going to load a given address into whatever register you tell it to. And then branch and link, if any of you have taken 2340 and you know MIPS, then it's the same thing as jump and link, where you set the link register to the address of the next instruction. So if you've got this instruction, you're going to say, come back here to the next instruction once you finish whatever other label function that I give you. This doesn't make any sense right now. It's going to make sense because we're going to use all these things, and I'm going to explain why they matter. Again, I probably should have prepared a little more, but that's okay. Anyways, so these first instructions right here, we've got the push. If you'll remember, this is going to push R4, R5, R6, and the link register onto the stack. We do that because we need those registers to do stuff. We need space to operate on all the data that we're dealing with. But R4, R5, and R6 are kind of just generally agreed upon by people who write ARM. Those are going to be callee saved registers, caller saved registers. The point is, we don't want to mess with whatever values are in there because they're probably important. So we're going to push those onto the stack because later we can pop them off and we can have those values again. But right now, let's just put them away, don't need them yet. LSLS and LSRS, we're not going to deal with these right now because they will get filled in automatically, but just know that they have something to do with this function parameter right here. Yeah, let's look over here to the left real quick. So we've got an array of U8s, that's unsigned 8-bit integers, nothing crazy about that. And it's got this funky name because that's what happens when you automatically decompile stuff, is you get funky names because you can't really tell the computer what all the variables mean, and we'll get to that later. We've got a function definition, we've got a define null 0, and then we've got this function, and this is what we're going to be filling in. So let's look at this LDR. So what it's going to do, if you remember, LDR is short for load address, and it's going to load this address into R5. Oh yeah, and then, so this is a little bit of help. This is a comment right here. And the hint is that this address is the address of this little U8 array that I showed you up here, right? So whatever the first instruction in our C function does, it's going to do something with this array right here. Okay, this add is essentially a copy operation. So remember that this first thing is going to be the destination. Whatever result of the operation happens, it's going to be stored in R0. But all we're doing is getting the value in R5 and then adding 0 to it. So it's basically just a copy operation. We're going to copy the value from R5 into R0. Why are we copying stuff into R0? Well, like I mentioned before, R4, R5, and R6, those are like generally agreed upon to do something special, or they hold special data. Same thing with R0 and R1. Those are generally going to be for return values and function parameters for when you call stuff. The reason we have all these like loosely generally agreed upon things is because the CPU itself is not going to enforce any of this, but if people don't follow those conventions, then nobody's going to be able to read each other's code, right? And the same thing with this move instruction. It's also moving this value hex 24, which would be 36, the value 36. Again, we don't know why 36 is important, but we're literally moving the value 36 into the register R1. So, don't really know what's going on, but those are in R0 and R1, which we said, those are for function call parameters, right? So those are pretty important. We kind of know what's going on. We're probably going to call a function, bam, BL. You guys know what BL stands for? Branch and link. Pretty sure. Branching, that means we've got a function call, which is exactly what that is. Look, those are the same function names right there. So we know that we're going to do a function call. So, I mean, let's write this out here. Copy, paste. But if you'll remember, we just stored values into the function parameters, or the generally agreed upon registers for function parameters. So there's a really good chance that our first parameter is going to be this array, and our second parameter is going to be the value 24. And if you look up at the function definition, look at that, a U8 array and a signed 32-bit integer. So watch what happens if we put in that and that. Oh my gosh, we just got to 28% matching. That's crazy. We figured out a quarter of the entire function just by looking at a couple lines of assembly, which is really cool. And again, let me remind you, we just wrote code that compiles to a chunk of matching assembly to this disassembled binary that we've been looking at. So that's pretty cool, and this is like the heart of disassembly. If I run out of time, I'm going to skip over the entire thing, but hopefully I can get to the entire thing. So after the branch and link, it's going to call this function that we don't care about. We're going to pretend that someone else already decompiled it. It's going to call this function with those parameters, and then it's going to come back with data. A void star. We wish we knew what was in there, but we don't. So it's a void star. We don't know what data type it's going to be, but let's just ignore that for now. So we've got this function, right? And right after the BL, we have this addS, which again, that's doing the exact same thing it did up here on line 8, is we're going to copy the value from R0 to R4. And if we're going to be copying, remember, I said R0 is for function parameters, it's also for function return values. So whatever this function returned is going to be an R0 at the end of it, if it returned anything at all. It might not have. But it's a void star and not a void. For those who don't know what C is, I'm very sorry. But if it was a void, it wouldn't return any data, but a void star, it's going to return some data. So we know it's going to return some data, so let's store it into a value. Let's put it in a U8 star, and we're going to call it temp1. And because the compiler thinks it's returning a void star, we're going to cast it to a U8 star. Still 28.4%, nothing crazy. But the reason we did that is because we saw that the binary needs to do something with the data because it copied it into another register. So we did that, boom, done. And the next instruction, it's going to compare R4 to 0. So whatever this value that we just took from our function, we're going to compare it to the value 0. And then we've got this BNE, and what BNE is, branch if not equal. So while this was a unconditional branch, which means it's always going to run this function, BNE is a conditional branch. So it's going to go to another location if the condition is true, and the condition being is R4 equal to 0. So let's write an if statement. T1 equals 0. The reason it's not going up in percentage, even though we are kind of working through it, is because the compiler knows that there's nothing inside this if statement, and T1 isn't actually getting used anywhere. So it's just optimizing out, which is fine. Once we do some more stuff, it will fill in those bits, but I promise you we are getting closer to the final answer right now. Sorry, let me read my instructions real quick. Yeah. Compare to 0. Okay. So, let's look at 20, which is where it's jumping to. So, if you look in here, so I mentioned the labels right here, right? you might notice that it's got this colon at the end. These are all labels, probably put in there by the disassembler just to help out with stuff. But yeah, so let's do that. So if t1 is not equal to 0, then we're going to do something right here at 20. All this stuff is what's happening in this if statement. So first thing we're going to do, copy R5 to 0. We've seen this 2 times by now. We know that we're about to call a function, right? Where R5 sorry, let me look at something real quick. Yeah, okay, cool. Totally not looking at the answer. Okay, so we've got this R5 value. Actually, the weird thing about this instruction is that it doesn't really do anything. It kind of will in a little bit, but
you want to apply code?
Oh yeah, sorry. Oops. So this add R5 in 0 and stored in 0, that's just kind of preparing to do something with R0. We're going to ignore it for now. Let's just generally ignore. Oh, sorry. I'm all over the place tonight. I'm sorry, y'all. R5 holds the address of our array, which we already looked at that. Okay. So you take the address, store it in R0. Okay, we're about to call another function with this array, right? 0x25, move it into R1. Again, we've done this before. We are probably going to call our function again. Look at that. So let's call the function. Let me just count this entire thing. And then stick it in 25. Boom, 47.2% match. We're getting closer, about halfway done. Let's keep going. Okay, so this is where it gets a bit tricky, especially if you're not familiar with pointers. We're going to do a left shift, we're going to do an add, we're going to do a load address, we're going to do another add. This is all a bit complicated. Who is not familiar with pointer math? Okay, got a lot of people who are cool with pointers. Okay, I'll take it a little easy for those who aren't familiar, but yeah, okay. So we're taking R6. We had this R6 up here, and we good? Okay. Remember what I said about these first two is that we didn't have to worry about the time, but they're generally going to be related to this parameter up here. Boom, we're using the parameter right now because we're dealing with R6. And so it's going to have something to do with param1. What else is it going to have to do with? We've got R4. Let's go back to where was R4? R0. Okay, yes. So we're going to deal with R1 and R4. Someone asking something? I feel like sorry. Have I been up too late? Am I hearing voices?
I hear it too.
Okay. We're generally going to do something with R4, and R5 is where we loaded this data into, the address of the array. Oh, sorry guys. Let me look one more time. Yeah. Okay. Unmute. Okay. Okay. You'll remember T0 is holding the return data for this function, and we found that back up here. And we can see that, so we call this function again, and we're using R0 down here. So let's store it again. Let's do another temp same amount of completion, but that's fine. And you'll notice, okay, we're kind of at the end of the function here, right? And these 4 instructions, this is what we're really having some trouble with. We know that we're right at the end of the function, and we're returning a U8 pointer, an integer pointer, which could be a list, it could be a pointer to an integer, it could be a lot of things. It turns out we don't actually have to know. So we're going to kind of ignore this left shift because what it's really doing is upscaling the value that's in R6, which is this parameter right here, to the width of a pointer, which, that it depends on the platform how wide your pointers are, but that's just something the compiler is going to do on its own. We're not going to worry about it. What we're really concerned about here is this add R1 to R4. So if, let's see, R4 is our address, and R1 is whatever we got back from this sub function. And because we're at the end, like I said, we know we're going to return. That's what we're going to do. We're going to return R1, which is what we got back here, and then we're going to be adding something to it. What are we adding to it? I don't know yet. But we know it's something to do with R4, which again stores return value from, let's see. Oh yeah, remember R4 currently has this T1 value in it. Again, sorry for all the naming conventions, but we are going to be adding something to do with T1. I'm doing some pointer magic here, don't worry about it. But the value that we're going to be adding to it is, let's see, R6. Storing that in R1, Pretend this makes sense. Again, I wish I had picked an easier function. I looked really hard, but it turns out people 20 years ago didn't write any better code than they did today. So this looks a little crazy, but the point is that T1, we got an array out of this. And what this return statement is doing is the exact same thing as this statement is doing. So this is actually a convention that your compiler is going to do for you, but really it's just hidden pointer math. So bada bing, bada boom, that's a little cool. Okay. So, but we're about 65% in. Now, we're at the end of the function, we already returned, so that's it, we're good, right? Except we've still got these things right here. This is our branch, this is our T1 not equal 0. So what's this move S R00? What's that, David?
That line doesn't compile.
Which line doesn't compile? The return statement?
Yeah.
I'm aware. I'll get back to that. Promise. What's up?
I'm guessing that the decompiler behind this is Giga.
Whoever disassembled this, I'm not sure what disassembled it. As for decompiling, that's what we're doing right now. Are you talking about? Sorry.
Sorry, you're right. I got you. I misunderstood. I thought this was like JavaScript that was going out. To something else.
This lives on someone else's computer. I'm sending requests to get compiled output, but anyways. So this is our branch right here, and that branch, if this condition was true. So now we've got if the condition is false. We don't really have to write this else statement, but I'm going to do it anyways. And it's going to move the value 0 into R0, and then it's going to jump all the way to the end of the function. Well, we know what R0 is. It's for return values, right? So it should be that simple. 83%? Oh my gosh. That's crazy. Okay, so let me zoom out again because I can't really see. Yeah, so we've got one issue right here. Mute one more time. The short answer is that this is due to, it's just due to compiler BS, doing its own weird things, or it's due to people writing bad code generally. What this is doing, shifting left by 1 is going to multiply by 2. This R1 was our return value for all this stuff, pretty sure. Again, this is going to seem like magic, but really it's just people writing bad code. Should return to... Ugh. Oh, yeah, I did it the other way around. Oops.
So is the issue here, the original code was like implicitly asking between different types?
Yes.
That's
Yeah, exactly, right? And that's the challenge in decompilation is you got to deal with someone else's bad code from 20 years ago. Anyways, look at that, 96%. This last little bit of short stuff, we're just going to ignore it and leave that for other people to deal with. But I don't know. I know I portrayed that process very poorly, but I think you generally have somewhat of an idea of how decompilation works. Is, you know, if you have a really good understanding of assembly, you're able to look at all these instructions that map to these higher level concepts in languages that humans still write these days. Anyways, here's the solution. It's exactly what we had. Yeah, before I go on, does anyone,
Yeah, so I guess this is really good to know how it works, but why wouldn't I just use Giga?
why wouldn't you just use
For
Giga?
those that don't know what it is, it automatically compiles a lot of these things and converts it to C code for you.
Very good question. The answer is because Ghidra doesn't always provide matching code, and when you're dealing with old video games from the 90s, not everyone used standard C compilers, which is really frustrating because Ghidra only supports standard C compilers. Or it'll support whatever assembly you give it, but if that assembly was written in a different way than it expects, then it's not going to spit out the same source code. So you could decompile old games with Ghidra, and you would get something that still probably compiles to the same sort assembly, but it won't match. It won't compile the same assembly, but it'll do the same stuff. So it'll be optimized different, or it'll be longer or shorter. Or anyways, that's what we're worried about. Is we in this scenario we want to do matching decompilation, where we write code that gives us the exact output binary. And here I'll talk about how did I go full screen? I forgot how I did that. But anyways, yeah. So what? That code snippet that I just showed you was from a Game Boy Advance game called Mother 3.
Come on, Reggie, give us Mother 3.
And I picked this example because it was easy. Big air quotes on easy. But if you, I still can. I might show that at the end. You can decompile better games. It's harder because they're on more complicated systems that do harder math and all that. I'll show this at the end, but over the summer I worked on an Ocarina Time decompilation project. Again, that was N64. Actually, all the decompilation has been done. I was mostly documenting and modding, but anyways, yeah. The goal behind these decompilation projects is we've got a couple goals. Primarily, people want to mod old games because people like doing that for some reason. People want to preserve, so companies on multiple occasions, like you'll hear about, BBC throwing away all its old Doctor Who tapes because they didn't have the physical space to store it anymore. Video game companies do the same thing. They'll throw away all their old code. I mean, I think someone pointed out that it might have been the Wii or the Wii U. but on their virtual console copy of like Super Mario for the NES, they had to pull a ROM from online because they didn't have one to provide, which is great. Like, if anyone has a ROM for the original Super Mario, you'd think it would be Nintendo, right? Apparently not. So if they're not going to do this, then someone has to, or someone should. And so preservation, that's a goal here, is we want to be able to preserve things and make sure that they can still exist in a very accessible format. And then understanding the development of the binary. That is less straightforward. When you perform a decompilation like what we just did over an entire game, or any sufficiently large code base, you are without a doubt going to start to understand the design patterns that the organization has, and in some cases, the design patterns of specific developers on the team. One thing that's crazy that I loved about the Ocarina of Time decompilation team is that they figured out, like, the guy who worked on all the bosses, his name was, or a lot of the bosses, his name was Moriata, and they found out that he also wrote the fishing minigame because the code was written so similar to the boss code. I don't know how they figured that out, but they did. And I'm pretty sure someone confirmed it. I forget where. But anyways, stuff like that is crazy. The fact that you can pinpoint the design patterns of specific developers by decompiling their code, I mean, it just provides a whole lot of insight. And so yeah, and the other thing is, if you can decompile one binary from an organization, chances are all their other binaries are going to be pretty darn similar. So the work from one will help you a lot with the work for the other one. And you see that a lot when, I mean, people are still decompiling Majora's Mask, but it's gone a lot farther because, you know, it's like the same game basically, like the engine is reused. So that's cool. So what? Who cares? I don't care about modding or preservation or any of that. Well, so yeah, if you just want to look at the security aspect of it, what's the point? Is it a red team? Is it a blue team thing? The answer is a little bit of both. If you're going to do red team decomp, you're going to be looking at someone's software to figure out how to break it. And again, you can do that with Ghidra, but maybe for some dumb reason you really want to get a better idea of how it works, or maybe you want to provide a binary that looks so similar that it could infiltrate someone's defenses or something. I don't know. I haven't done any red team decomp before. But blue team decomp, which is probably a lot more common, would be like reassembling viruses or, you know, any kind of malicious payload, just to figure out, you know, what vulnerabilities are being targeted, so that you can fix them, right? So that's why it matters from a general security standpoint. And what we just did is the easy part, believe it or not. Like Peyton mentioned, non-matching decompilation can be automated really easily using big public software like Ghidra, or slightly better closed source paid software called, there's one called IDA. But how useful is doing that if you want to accomplish the goals that I just talked about? Let's see what automatically decompiled code looks like, again in the context of Ocarina of Time. I'll show you how big this file is. Yeah. What is that? 14,000 lines? That's pretty darn big. This is the player controller code for Ocarina of Time, so it handles movement and attacks and all that. But man, I can't tell what any of this does. I mean, okay, there's some item actions, blah, blah, blah. But look at all these unnamed function calls, unnamed variables, unnamed animations. Like, I couldn't tell you what any of this does. And I challenge any of you to tell me what it does. The trick with decompilation is not the decompiling, which does take a lot of time, but it's a relatively straightforward practice that people know how to do. Documentation is where it really gets hard. You can't just perform matching decompilation to get an idea of everything. You still have to like name functions. You have to figure out what they're doing. What's all this data going around? You know, what does it mean? you have to figure that out if you want to figure out, you know, anything about the structure of the code. And yeah, you know, if you look at any of these functions, I mean, you can't tell me what any of them do. Has something to do with the sword, maybe. Again, this is something that people did document. I picked a really old commit from last year to show this off. It looks slightly better now, but player is still known as being one of the less documented files. And yeah, so the Ocarina of Time decomp project with, I don't know, I think the team was probably 5 or 6 very dedicated people and maybe like 10 less dedicated people. It took them about 2 years to hand decompile the game. What's up?
So how do you get better at documentation? Because it's not like,
You just do it. Again, you know, because especially long ago when C was still not really suitable for game development, everyone had their own styles, everyone had their own compilers and stuff. So if you want to document an old game, you really have to like get into it, and you start with little functions that you can kind of tell what's going on, and then over time you just learn more about how the code runs, and you get a better idea of where all the data is going between. And yeah, so it's really hard to give you a straight answer, but the only way to get better at documentation is to just do it. And yeah, so even while the game was being decompiled, so that commit I showed you, at this point in time, the game was still partially in assembly. So while it was being decompiled, people were documenting it. They started 2 years ago, and to this day, it is still being documented. They finished last November, so we're coming up on 1 year. But as someone who has documented a fair chunk of the code, like enough to know what I'm talking about, unless we like double the amount of people working on documenting the game, I don't think it'll be done for like 2 years maybe. So roughly 50% longer than just hand decompiling everything. Then again, it might get more popular and people might fix it sooner. I can't give you an exact answer, but that's just my estimate. What's up?
that's like really to our previous question. So when you got started, did you like look through everything that's been documented and try to go from there? Or?
So when I started, this was either the late June, early July, and so with the decompilation finished in November, it got a lot of press. Like Ocarina of Time is a very, very popular game, and when news outlets heard that this game has been decompiled, the first thing is that you can do a PC port with it. So everyone got super excited about that. So anyways, it all got a lot of press, and by the time I joined, roughly 6 or 7 months after the decompilation was finished, there had been people who started to document a lot more. So I came in right, and like all the teenagers were out of school and everything, and I was too, but I had a job. But it was kind of like a little renaissance, because there was just enough to really do some cool modding, but there was still a lot left to document. I don't remember what your question was, but I hope that answered it.
Yeah, like how you got started.
How I got started? Yeah, so I found a little niche, and I found a chunk where I could start modding, because that's what I wanted to do. And then as time went on, I started dealing with systems and like certain NPCs that were interesting, and they weren't completely documented, but in the interest of my own modding, I documented them so that I could work with them better. And then I go and push that to the main repository. And so yeah, I've documented a few characters and animations and stuff. And one thing is you should be pretty good at Blender to know what's going on, because people have worked out how to import all these models into Blender and Autodesk and all that. And so that's a good way to figure out what animations are, because otherwise you'll be just reading code to figure out what all these animations are, when you could just be looking at them to describe, to document them and stuff like that. So yeah, that's how I got started. I got started because I wanted to mod it, and then there was stuff that wasn't sufficiently documented, so I documented it. More on documentation. Some aspects of compilers and certain program features make parts of documentation a lot easier. For program features, teleport me blind. Yeah. This is a log statement that someone at Nintendo wrote, and conveniently, they used a string literal for the name of the file. So we know the name of all the files in the entire project. Well, almost all the project, almost all the files in the project, because there's log statements in all of them, which is pretty cool. The other thing is that embedded in the binary, the entire project directory structure is embedded. So like all of this, all these folders, I mean, these are the original names of the folders that Nintendo had forever ago, which is really cool. I mean, that's just something that the compiler decided to do. It didn't have to do that. It left them in there as comments. Like, that's just really convenient for us as decompilers. But what's up?
So you got a header file there. How does decompilation handle, or when you're doing it by hand, how does it handle the generation or the relationship of header files to C code?
I could not tell you. When you're defining a function, like, that's not a function. When you're defining a function, like right here, generally what's happening in a compiler is it will internally store the name of this function and then whatever parameters it requires, and it'll just hold that in the compiler's RAM until it sees a statement in the code that calls this function, and then that's when it will write out the label for the function, write out all the logic for the function, and then like this right here would convert to a hex value in the assembly file. It's somewhat complicated, and it would depend on the compiler because they all do things differently. Again, this was compiled with an in-house Nintendo C compiler, which is kind of, I can't believe people used to write their own compilers for their company. And believe it or not, it was because GCC wasn't good enough at the time. It would not generate code that was fast enough. And that's crazy for us to think about because everyone knows C is the fastest. But it didn't used to be, which is like, that's absurd to think about. I mean, for the NES, for the SNES, and for some N64 games, people were still writing in assembly just because they could write better than a compiler. Crazy to think about, but...
So what disassembler did you use for this?
I did not disassemble this. This is from the Mother 4 disassembly, maybe Mother 3 disassembly. Let's see. Wait, that's not it. Maybe they'll tell us. This is it.
You've given me enough to go find it.
Okay.
Appreciate it.
Yeah, no problem. You could use plenty of different programs to disassemble. You could probably write a disassembler pretty easy, I think.
You can, but it matters. You can, but it matters a lot. Like the algorithm, that's what I work on, and the algorithms you use for disassembly matters a great deal.
Sure.
Especially if you're trying to do this kind of stuff, because the errors are fractory. Like they propagate throughout. Like if you disassemble an instruction wrong, right, the stream is fucked for however long it takes, depending on what the architecture is. Right. So
couldn't tell you.
We're
Oh yeah, Nintendo's C compiler is called IDO. Anyways, legal issues. Can't have anything good without getting lawyers in it, right? Believe it or not, Nintendo does not like the idea that we can rebuild their games and modify them. Big surprise, right? But it's kind of a gray area because you sold me the cartridge, which had the binary on it, like flashed, and I ripped the binary from the cartridge with a machine that I bought or built or whatever, and now I've got a binary file that I bought from you, and then I run it through a disassembler, which is a free program, and it spits out assembly that was from a binary that I bought from you, and then I write C code that happens to compile to exactly the assembly that you wrote, but I wrote that, so that's mine. So why is it a gray area? Who knows? But yes, that's why it's confusing. But the other thing is that the binary doesn't just include code, it also includes assets. So the 3D model is obviously Nintendo's. Like, there's no disputing that, like, the Mario model is theirs. I can't say that I got the data for it, so it's mine now. That's not how it works. And so the answer to that is that decomp projects, like the Ocarina of Time decomp and Super Mario 64 and all that, when you download the code to generate your own copy of all this decompiled stuff, you get the copy of all the code, and that's what I showed you on GitHub, but you have to provide your own ROM that they have an extractor script for. So it'll extract all the assets, and of course we trust that everyone goes and buys a cartridge and rips their ROM and doesn't go online and download it, because that's very, very illegal. And the funny thing about the Ocarina of Time decomp is that it uses the GameCube Master Quest debug ROM, which you can't obtain legal. You can't really get the disc anymore.
We have one on
And-
campus.
We have it on campus. Oh,
there.
that's cool. But don't tell Nintendo this. I downloaded mine from a YouTube comments section because you can't get them anywhere else. Like they're hard enough to find on the internet, because anytime they get put up, Nintendo takes them down. And yeah, does it solve legal issues? No, not really. But so far, there has not been any Nintendo decompilation project that has been taken down. So it probably works, but everyone who's working on these is very aware that they're on thin ice. If you make a misstep, something bad's gonna happen. Like right here. For those who are in the know, you might have heard about the Giga League, which it was this big Nintendo leak. I don't know exactly how it happened, but someone broke into Nintendo headquarters or something and found out a bunch of data about basically everything Nintendo's worked on for the past 30 years. So a lot of stuff. I mean, we got information about new games, we got old code bases. So a large chunk of the Ocarina of Time code base, the original one, is included in the Giga League. So this is code that they wrote. So, you know, with decomp, I wrote the code that compiles to the assembly, that compiles to the binary, that runs on your machine. Like, you can see the cohesion there, right? But you definitely can't use code that Nintendo wrote, because they wrote it, it's their IP, whatever. Believe it or not everyone agrees on this. So, while I was working on the decompilation, there was this big controversy with this 14-year-old who almost ruined it for everyone, because he did decompile a lot of the game by looking at the Giga League, which is very much not allowed. Like, it's like a known rule that you're not allowed to work on the decomp if you've ever seen anything from the Giga League, because you're just inviting Nintendo to come shut you down, right? But the issue is that this dude did a lot of the decompilation. I think he did something like 20% of the entire project, and he did it at the beginning, which means that everyone else built on top of his, which means that they kind of got poisoned too, because they are looking at something that someone else looked at the Giga League for, and it just ruins the whole clean room point. Like, and there's this big issue. Do we uproot 80% of our progress? Like, do we start over because some jerk ruined it for everyone? Do we just modify the top level and then tell everyone not to look at the history? Or do we do nothing?
Code just happened to be the same as the leaked code.
You can't say that. That's not allowed. You can't. I mean, if it's the exact same code, then I mean, a court's not going to allow that. Even if you like change all the variable. Well, not if you change all the variable names. Maybe. No one's ever gone to court for a decompilation yet, so we'll figure that out eventually.
It's not true.
Hmm?
not in the sense you mean.
What do you mean?
I mean, I'm pretty sure the Oracle trial revolved around some amount of decompilation.
Really? Okay.
Because it specifically with like variable names and stuff like that.
Gotcha. Well, I didn't know that. Oh, more
I could be wrong.
I don't
It was
know.
a while ago I do drugs, so.
Cool. Well, yeah, and then the third option is do nothing, and then just say that this guy did leaks, but don't you do them. And then, like, anyways, the issue is that they've all got each of those solutions has their own issue. Nobody ever agreed on what to do about it. I remember taking, like, weeks to vote on what are we going to do about this guy. Like, we already banned him, but we've still got all of this code, like, and I think the conclusion that we came to is do nothing but tell people not to do it in the future. And it's like, I mean, that worked pretty well. He was the only guy, but
Can you report him for academic dishonesty?
I mean, if we draw any attention to him, we'll just get Nintendo on our asses, and they'll take us down for what he did, which would suck for everyone. But yeah, so it's really just an honor system. I hope none of you go and use Giga League stuff. But anyways, that's the end of my talk. If anyone has any questions. Questions? Anyone? Nothing? How much did everyone understand the ARM thing? Yeah, you don't count. Who definitely did not get any of it? One.